All right, so let's maybe start. So hi everybody again. So as was requested by the team, I think the last retrospective and review meeting is that it would be good for us to have technical discussions where we would discuss certain technical aspects. What is requested by the team. So what we agreed that we will have with Dagi Meluk and Janina is that we will be having these technical discussions or technical hours. So for now, the team asked or requested these discussions around 3 topics. One of them is the topic of today, which is P2P networking and NuNet. Another is NuNet architecture. Today the topic is P2P networking, which Dagim will first make a presentation or talk, and then we'll discuss it and I'll answer the questions.
Okay. So I think I could start with the documentation, right? At least a general overview of. Can you please allow me to share? Okay. So let's start from the documentation, and so I'm skipping why the need for the peer-to-peer, but if it's necessary, since we're going to be using personal computers for compute processes, we're going to need a way to communicate with them directly. So on a typical internet communication, where, for example, you access a website, you can see the website from your computer, but the website cannot see you because the devices that we're using at home or office are located behind NAT devices. So those NAT devices are what make us required to use a peer-to-peer network. That is, we're going to have to give each machine, which is a personal machine, an address to communicate with, because these devices do not have IP addresses or public IP addresses. They can have public IP addresses, private IP addresses, but not public IP addresses where it's accessible from anywhere. Okay, so that's the need for having a peer-to-peer network. So when working during the private alpha, we selected using PyIPv8. We actually first attempted to use regular WebRTC, which is what's used for video communication these days with Zoom or with any of the video conferencing applications. But PyIPv8 was exactly what we were looking for. The library provided all our requirements. So, for example, one is encryption during communication. It's very simple to use. WebRTC is a bit too much. It's really big, and it's also fully written in Python. There is no other programming language that PyIPv8 is implemented in. And the third one is, we can. Actually, it's the simplicity, because we can use the public keys of peers. So we're going to call every device a peer within the network. So we can use the public keys of those of the peers as an address to be able to communicate with them. So you can go to this repository. You can get the documentation from here. Okay, so let's start from the examples. Okay, I have actually prepared them somewhere. Here, go here. It would also be good actually to talk about NAS devices. I can send you a link to this paper. It's about peer-to-peer communications. Basically, it explains the most popular method of doing NAT hole punching. But just to take the main ideas from it, I've highlighted what is important here. Network address translation causes well-known replacements for security communications. Instead, peers involved may not be reachable at actually they are not reachable at any globally wide IP address. And 82% of NATs that have been tested by these people support UDP hole punching, and 64% support TCP. With PyIPv8, I think we're using UDP punching. We can check out the code later when we go into the NuNet adapter to basically see how it was written. And yeah, there is actually it has good diagrams to show how the NuNet punching works. This is, we'll come back to this later. So basically, the NuNet punching is going to basically work by, for example, let's say we have these two clients. So this is client A and this is client B, and actually this is when they share a NAT device. So let's look at when they don't. Yeah. Okay. So let me go to just Google once, and let me Google my IP address. So this is the IP address it's going to show me, 196.188.75.100. But if I do, let's say, IP add to my computer, I'm going to see that my IP address is 192.188.1.3. It's different from this one. So this is IP address of the NAT device that my computer is behind. So whenever I use a website, this is the IP address they're going to be able to see, not this one. This is only for the office that I'm working in, and this is for the rest of the internet, right? So when we come to this diagram, the IP address we saw on Google is the address here, the NAT device, and the client A here, the 10.0.0.1, is basically going to be my private IP address, right? Not exactly, but just for the sake of this diagram. So the hole punching is basically going to work when the two clients that would like to communicate with each other, they would send their private IP information and their public IP information to a central server. So there would be one central place that would keep these records. So yeah, actually, when you use NAS devices, basically what they do is they would assign, they would keep a table of IPs and ports to much. So what the NAT is going to do is basically it's going to allow you to share IP addresses, since there are very little number of IP addresses, right? So basically this IP address is going to be shared, the 155.99.25.11 is going to be shared among multiple devices, but for each connection that each client is going to establish, separate ports would be provided, right? So when you establish a connection with server S and you tell it, you supply it with your own private IP information, that means this is the session that you're going to establish. Session A between S is going to be this is 18.181 is the IP address of the server. So in order to establish this connection between server S and client A, the server S is going to know about the NAT device, the port it has allocated for your connection, and the port the server has allocated to receive your information. So client B is going to do the same thing. Then what server S does is it's going to supply client A with information about session about client B, and it's also going to supply client B with information about the session with client A, so that since these NAS devices have already opened these ports for a session with server S, once that information has been supplied, then client A and client B are going to attempt to communicate with each other, bypassing the server just by using the information that was supplied. So now client B has the NAT device and the port number that was allocated for that session. So when client B attempts to connect with client A using that port, and when client A attempts to connect with client B using the session that its own NAT has allocated, then at some point, those when it happens basically at the same time, the NAT devices might allow the session to pass through. They might not allow it, or they might allow it, but it works when the attempt is correct enough. So when it's at the right time, or and when you're using the right type of NAT device. So if it's established, then at that point, server client A and client B do not need server S. They can just basically send information through their NAT, and their NAT is going to basically communicate with the other NAT that client B is in, and the communication will just go bypassing server S. So this is going to be how the NAT hole function is going to be established. So this is the critical point where the symmetric NAT issue comes up. So so there are several types of NAT devices. So there are NAT devices that would basically maybe allow a specific IP and a specific port combination to be connected to in reverse, or maybe it would be a specific IP address and the destination port, or it can be the source port and the destination IP. That basically with different combinations, you're going to have different types of NAT devices. So the key one here is the symmetric NAT. So an explanation here is a NAT that is only designed to support client-server protocols will not necessarily preserve the identities of private endpoints in this way. Such a NAT is the symmetric NAT. And there is an explanation. For example, after the NAT assigns the public endpoint, this port number 62,000 for client A session that we saw earlier, then the NAT might assign a different public endpoint, such as 66001 to the peer-to-peer session that it tries to initiate with PB. That means that the first session is not respected, and when client A and client B attempt to establish connection with each other, then it's going to fail because now a new port has been allocated. So that's the problem with symmetric NATs. And when the paper was beginning, it talks about the option to relay. So even with WebRTC, which is how you communicate for video conferences, it uses a protocol called Turn protocol, or a Turn server, which is basically going to relay the communication between two clients that could not establish a peer-to-peer connection with each other. So similar to that, what we did with the NuNet adapter is to have a relay node. So let me just do a test here. It's going to be difficult to do this test because I have two networks. Let me just run this one first, and until it finishes, let's go back here, and it says relaying always works as long as both clients can connect to the server, and which is always the case. All of us can connect to a centralized server. So that would basically mean relaying the message through that central server when two devices cannot establish communication. But the downside of that is that the server is going to be, where is it? It's written here. Okay, its disadvantages are that it consumes the server's processing power and network bandwidth, and communication latency between peering clients is likely increased. So yeah, okay, so currently I'm behind a restricted NAT, but I have another network which is behind the symmetric NAT, but I don't know if I switch, the internet might, connection might go away, but actually the Wi-Fi is the symmetric NAT. The line I'm connected to is the connection behind the restricted NAT. So let me just try it again. Now it's full code. I think if I disconnect the Ethernet line, the Zoom connection would terminate. But maybe we can test later. Can switch to the symmetric NAT and see how the peer-to-peer network does not work when we get to the demo. Okay, so that's about NATs. Yeah, so let me go back.
Sorry, little question.
Yeah.
Both the Wi-Fi and Ethernet, are they not on the same router?
No, they're not. That's how they're going to be on different NATs.
All right.
One is the Wi-Fi is through a wireless 4G network, and the line is through a fiber optic cable. They're two different networks. Oh, so other questions?
Sorry, so if you do, since you are connected to the Wi-Fi now, if you check your public IP, it's a different one, right?
Actually, yes, that's the key. It might not be different because I think my computer prefers to use an Ethernet line rather than a Wi-Fi, so it's still going to be the same, I think. But let's check. Don't remember the previous one. I think it's the same, right?
Yeah, looks.
Later on, perhaps we can disable the Ethernet one. I think the computer prefers to work through Ethernet since it's more reliable. So even if the Wi-Fi is connected, it's going to go through there. That's why actually the Zoom connection doesn't terminate when I turn off the Wi-Fi, because it's by default going through the Ethernet. So if I reload this, I'm still going to get the same answer here. So let's just connect for now and test it later, maybe at the end of the meeting. Okay, so yeah, if there are questions, just ask anytime. Okay, so documentation is doesn't have a lot, but yeah, it gives enough to start with, especially how the library is supposed to be used. These two examples I don't recommend a lot because they do not show a lot about it. But maybe perhaps let's try this once. It shows the default configuration. Let's just copy it somewhere and yeah, I've prepared one. Okay, two of them, so we can check out after this one. So let's just paste this here and select the imports. I think I copied here. We're switching to virtual environment. So let's one key thing is okay, let's go through the code first. Okay, yeah, this is just going to display the configuration, so it doesn't matter that much. Because a new session would be started, and it's just going to show the configuration. So let's just run it. We can go through the line by line for the next ones. So overlay smooth. So just shows the data information about establishing the connection. Actually, this is irrelevant. Let's say a different one. Yeah, now this would be good. Okay, so we can go line by line here. Okay. So the whole concept of IPv8 is overlay networks. So first of all, the peer-to-peer network by itself is an overlay network. So there is a real network, the IPv4 network that we normally use with the four number IP addresses. But this peer-to-peer network is going to be an overlay network on top of that. So everything that happens in IPv8 happens with overlays and communities, actually. Best to call it a community. So you're going to have a community ID for every community that you're going to work with. So for example, if we go to the NuNet adapter code here, so for the adapter, we're going to have a community address at some point. Yes, a community ID here. For the discovery one, we're going to have another one. So when the deployment is a test and when it's a production one, we're going to have different IDs. There is a third one somewhere. Yes, for relay. Where is relay? I think this is an old code. Yeah, this is one. So we're going to have a NuNet relay community, which also has its own community ID. So the community IDs are central to establishing communication with other peers. So when you're in the same community, you're with another peer. That's how you're going to be able to communicate. Okay, so what this demo does is it's going to create a class. It does nothing at this point. It just creates a random number for the community ID, and we do a loop and create two peers. The first thing you have to do when you create a peer is you have to create a key and register the key. So here, what it does is, since I is going to be either 1 or 2, the key is going to be ec1.pem or ec2.pem. So we're basically going to have two peers on the same computer. Then when you add the overlay, you're going to define the community name, the peer. Basically, this is going to be the key related to the person created. The introduction or working strategy, how many peers we're going to look for, timeouts, then the bootstrap definition. We'll see about this just in a second. Then you're just going to start the community. So most of IPv8 is asynchronous. So basically, if you're going with an peer-to-peer network, you're definitely going to have to work with asynchronous code because it's not determined whether you're going to have communication established or your message transmitted or anything. Okay, so let's run this one and overlay 3. So this is going to be overlay 3. Sure. Let's correct the import. The tutorial assumes basically that you cloned the GitHub repository and import it from there. Instead, I have a virtual environment where everything is installed. Oh, there is no. Okay, this is also useless because there is no printing. Okay, let's see a different one where there is a printing. But if I do ls now, I'm going to see ec1.pem and ec2.pem, which are the keys that's what generated by this. Sorry, this was a useless one. Yes, this is the first one, and I have one prepared here. Print peers. And what I did is I put the adapter community ID from the NuNet adapter from here as the community ID. So we will be able to see other devices as well when we run it. I also removed the for loop that would create multiple peers on the same computer. So there is only going to be one peer that would be created on this computer, and it's going to look for other peers within this community ID. One thing I should have talked about earlier is the idea of how does a connection get established. Sorry about that. So let's go to the code. And inside IP-bit, we have a configuration module. So in this configuration module, the IP address and port pairs that you see here are for bootstrapper servers. So these bootstrapper servers basically serve as, let's say, maybe a DNS address, a DNS server. So when a new peer joins a community and doesn't know other peers to communicate with, it's going to ask the Bootstrap server, what other peers do you know? And the Bootstrap server would reply with the address of a few peers. So basically, it's going to serve as the server S that we saw earlier. Not exactly, but it's doing the same job of introducing a new peer to other peers within the network. So these IP addresses that you see are Bootstrap servers that the Traveler by themselves have launched. But if you'd like to launch your own Bootstrapper server, and there is a script here, tracker plugin. So this is this would launch Bootstrapper for yourself. So you can just basically indicate the port that you want to listen in, and give it a go, and you can replace the configuration by the one we saw earlier. So when I launch this script, that's going to print all the peers it comes across with. The way it is able to establish communication with other peers first is by contacting the Bootstrap server. And we can see it here on this line when the overlay is defined. The default Bootstrap definitions have been passed to it. So okay, let's go line by line here. So let's start from here. So since we have an asynchronous function that's going to produce its results in the future, we have an ensure future, then start communities. So this is the function that we're talking about. Then give event loop, then run forever. So we then start communities. Builder equals config builder, then clear keys, clear overlays, just so that you don't have anything loaded. Then builder does add key, then a new key would be created. The overlay, overlay network that you want to use. But basically, on a typical case, we're going to see with the NuNet adapter, you're going to have multiple overlay networks. So I think it's in the documentation as well. Okay. Right. Okay, I don't know how it is, but it talks about how basically, by the way, Tribular is a torrent software, this one, and Tribular uses IPv8 for the torrent peer-to-peer communication, and they show in the documentation somewhere, maybe it's bootstrapping. At some point, they show how Tribular uses about 8 overlay networks to for the different functionalities. So for discovery, you have one. For DHT, you would have one. For file copy, you would have one, and similar. Okay, so this is just one overlay, but what I wanted to say was in a typical case, you're going to have multiple overlays doing different stuff. Okay, so we're going to start the community. Yes, we're going to load this my community class, which is this one. So this community class basically has a community ID member, data member. So we're setting that one here when we inherit from it. Then we also have a function where when the community is started, which is going to be called. So let's define a function called print peers. So it would say I am self my peer, its own address, and I know self is going to iterate over all the peers that it knows and print them. This register task is the IPv task manager. We can talk about this just after we see the demo of this code. Okay, so I think that's clear, right? You just load a community, you give it community ID. Edit something. Gives a community ID, and as long as it has the bootstrap definition, it would be able to find others. So
sorry, little question.
Yeah.
The bootstrap server is the ton server, right?
You can not exactly. I think the best analogy would be the Stern server. It makes the introduction. It doesn't relay the messages.
Oh, I see. Okay. I thought the ton server relays. Okay.
Yeah. Yes, the Stern server relays actual messages, right? So especially with the WebRTC protocol, you're going to have the Stern server to take care of all the message between two clients that are not able to communicate with each other. Maybe they're behind a symmetric NAT, or maybe they have a firewall or something. So the Stern server would carry the actual messages, but the Stern server, these protocols are both for the VoIP and WebRTC protocols. But the Stern makes the introduction and the Stern relays the messages. So an analogy with IPv8 would be the bootstrapper would be the Stern server, and the NuNet relay that we created a few months ago would be the Stern one, because it carries the actual message.
Okay, understood.
Okay. Right. Okay. Yeah. Okay. Let's run this one. So Python print peers is fine. So since it's in the adapter community, it's going to find other devices. So the first one, it's always going to say 00 until it even knows about itself. So as you can see, this IP address is the one we saw earlier. Oh, and this computer is the desktop computer that I have in front of me. Let me build that one. I should have been able to see other peers. There should be other ones. Maybe let's try. Yeah, let's try maybe. Let's copy the code and go to another server and try it again. Actually, best to copy from the edited one.
But basically, Dagim, here,
Yeah.
can I ask? Here, we should see all the servers, all the peers of NuNet that have NuNet adapters and that are connected.
Yes, that's actually why I'm curious, because I can only see one.
Right, and then actually, why do we see only internal addresses 192.168, etc.? Shouldn't it be like public addresses? Or it depends?
Actually, yes, it depends. Like it's how they advertise themselves, so it's going to be different.
Okay.
Okay, so let's make an IPv8. I hope I have. Discovery one. No. Okay. Now we change it. As you can see, it was first showing us I am with the address of the map. Right? Yeah. First, it was saying I am here, then 196.188.7500 with the address of the NAS device. Then it changes to its own local address. So now it's I am 192.198.1.3, which is the private address. Okay, let's launch it again here and see. Okay. Here. So it's also just starting. Let's make this one bigger. So the one on the left is my local computer. Okay, now this machine is able to see other peers. I don't know why I am not. But it's not fully deterministic. That's what's weird about it. Okay, so
but is it NuNet peers, or did you?
Okay.
Is it all these are also on NuNet community? On NuNet adapters community?
Yes, it's the same code that I just pasted.
Okay.
So
just sure.
Oh, okay. So this is the same code that I used on both. It's the same community ID and everything. But the peers they're going to see is going to be different. But I should have been able to see more than one at least here. So this one is seeing a lot. Let's make it bigger. Okay, so let's freeze it just a second. So there is 196.188.7500. Actually, that's me. So this is a server. Then it says I know 196.188.7500, which is this computer. Sorry. Which is this computer. Okay. It also knows other peers. So here you have the peer IDs. It also sees other devices. And this, oh, another one, because I actually have two devices here in the office. Oh, no, it was rearranged. It was rearranged. Let's check the peer ID. It's IIJ. And this one is, yes, I know IIJ. Actually, it's not seeing this this device. It's seeing the desktop computer that I'm using here. That I'm presenting on a laptop. We check with the peer ID, which is the same here. They both know another one, so this one is the AISBX. That's the ID, but this one doesn't know it. Let's check it. Yeah, it doesn't know it. But I think that's actually that's the case with it. We're not going to be able to communicate with everyone, but a few peers are going to be accessible. Questions here? Okay. So let's move to one crucial thing with this memory is, since everything is asynchronous and it's not a very deterministic way of doing things. They have a task manager that they built. So the one we saw here on this one, the line we saw here, self.register task, is able to work because every community is a task manager. Just a brief overview of what a task manager is. So just check out this normal asynchronous code, an example. So you have this completed array, an array called completed, and you have this function give me true, which receives variable here, waits 0.5 seconds and adds what it receives to the completed array. So what you do first is you run this function, right? Then you print the content of this array. So when this function starts running, it calls this function first with the value 1. So what would happen is it would receive 1, sleep for 0.5 seconds, then append the number 1 to the completed, right? So next, what it's going to do is it's going to wait for a second. That means it doesn't go past the lines until this one completes. But this one was not weighted since it's an asynchronous function, and this was not weighted, so it will just continue down the line. But it's going to wait for this one. So basically, even if this line comes after this line, the first member of completed is going to be true. Then after you have the true, without waiting for anything, you just have complete append 3. So the next member will be 3. Then you have a sync ensure future, excuse me for 4. This only ensures that this function has a future. It doesn't wait for it. So it just goes beyond. Then you have append 5. Then you have a sync sleep for 1, which just waits for 1 second, right? So the result is going to be, the correct answer is 2, 3, 5, 4, even though we added them as 1, 2, 3, 4, 5. It just becomes 2, 3, 5, 4 because number 4 was not waited for, and number 1 was not waited for. And even worse for number 1 is this happens very quickly, and it's not even waited for. So and equally important is that the answer changes to 2, 3, 4, 5 if you omit. Sorry about this. Okay, if you omit the final async, sleep 1. So if this,
I have a question.
yeah.
Okay. Can I ask a question here?
Of course, yeah, go ahead.
Okay, so let's assume there is a one task and there is another task, etc. So
Yeah.
technically speaking, peer 1 is going to have some kind of a conversation with, maybe he wants to send something, right? So if there is a deadlock, then what happens? How do you manage that?
No, not sure, because I don't know if we ever faced that. Because
when I was trying to get documentation, it's stated somewhere that you have to manage the deadlock. It inherently doesn't provide anything regarding that.
Not sure how we can manage a deadlock. Sorry, I don't know about that. Because I can't even imagine how it's going to come up, because we don't have peers sending messages to each other very frequently. Basically, they share a registry, which is the DHT that we use. So before you can update, the DHT, you would put a lock on it, update it, then just send it out.
Okay, so basically you are using the lock mechanism for deadlock.
So that was your question with the DHT? I was actually assuming if yeah, okay, I was assuming actual messaging, like basically send message to this peer, right?
I mean, normally what happens is, for example, if peer 1 wants to write something to DHT and peer 2 wants to read something, right? For example, we have a compute machine and we have the service machines. They have to be syncable, right? So if compute machine did not write something and services wants to read something, so that is a situation where deadlock happens.
Yes, that makes sense. But is that a deadlock, or that's more like the message consistency is not kept. So basically, what one of the peers is going to read is an outdated message.
Yeah, exactly. So that is technically a deadlock, because when someone wants something and it doesn't get something, it gets something else. So whole logic is flawed, right?
Yeah, but if you get a wrong one, if you get the wrong answer, then I think that's just not.
If I may, I think I can comment on this. This is basically the decision of the whole architecture in pretty much in decentralized networks and in peer-to-peer networks. And as Dagim said, even this one is non-deterministic. It's not that you will get all the answers depending. I mean, the same answers each time you run it, or each time you run it from the different peer. And so basically, you cannot, in general, guarantee that we will have consistent information across the network. And that is a design decision, because if we want that, then we will have deadlocks. But if we drop this one and we work, so basically, I mean, in actual usage, we will not use await at all. And the cost of this is that peers may get different information, and we'll need to have a different mechanism how to deal with that. That would be my kind of short answer from the architectural perspective, if that makes sense and answers anything.
Yeah, that makes sense. Basically, my issue was that, for example, it is right that in P2P networks, the information is not synchronized, or you can say the information keeps on changing, right? But we have to make sure that the right information is there at the right time, so that there is no miscommunication in the network as well.
Okay, so with miscommunication, I don't think we can guarantee that, but for some things, so what Terros did, let's say even with the DHT, is to use the global registry as a fallback, only sometimes. So, for example, when a new peer joins the peer-to-peer network, it's not going to have the full hash table synchronized. So there is about a minute or two where you don't have the full information. So if it's looking for a service at that time, and if it cannot find it, it's just going to go to the global registry and ask for the correct information as a fallback. So it's basically a solution similar to a timeout. Terros, are you here? Maybe he can. Oh, he's not here. Okay, so basically that solution is similar to a timeout solution where you're looking for something, maybe you know it's there, but if it's not there, then going back to a reliable source. But we can't always do that, especially because we're also going to get rid of the global registry.
Okay.
But okay, actually, what I'm heading to right now with this task manager is maybe related to that, to what you're looking for. So let's say you have a community for discovering other peers, you have a community for relaying messages, you have a community for sending messages or something, or whatever purpose. So the task manager that we're getting to now is basically a task scheduler, so that you don't have so that you don't initiate the overlay network or the community that should be initialized at a later time first, right? So it's a scheduler, and basically it also decides how it also decides your architecture of how you're going to use IPv8.
Okay.
Right. Okay. Okay. So with this function, even though we added 1, 2, 3, 4, 5, we're going to get 2, 3, 5, 4. And if we skip this line at the end, we're going to get 2, 3, 5, because the future ensured task is not waited for, so it doesn't happen. So yeah, okay, here it's explained. Another example. Okay, so the task manager. So basically, the task manager, what the task manager does is it's basically a task scheduler, and you can name your tasks. So to say an example here, so we have the same completed list array here, and we have the execute me tool. Basically, does the same thing as we did before. So when we start with task manager equals task manager. We just create an object from it, register task, the name, the function, the argument. Then if you'd like to cancel it, you can just cancel it at a later time with using its name. Then you can just wait for all tasks, and the task manager can actually have basically as you saw on the example that we just did here. It can also use intervals. So if you have a task that should happen in some interval, then you can define that as well. I think somewhere there is explanation of why task manager is needed. Managing future instances and coroutine instances is managing there is somewhere which explains why it's necessary, especially why they made communities task managers. Any community within IPv8 is also Where can we find? Okay, maybe let's. Just a second. Okay. Let's clone it somewhere and. So let's find the community class, and I wanted to see how they inherit from the task manager class. If we're able to see it as quickly as we can, then that would be good. If not, we can skip it. I think let's see. F12 and definition. Going to the definition is not working. It's going to be difficult to find it by hand. Maybe look in here. Okay, going to the definition is not easy, so perhaps it's we can do this. Yes, okay. So community inherits from the EasyPack class that we just saw. The EasyPack class inherits from the overlay class, and the overlay class inherits from the task manager. So every community that we basically inherit from, as you saw earlier with the here, as we saw here, basically when we create our own communities, we're just going to inherit from community. So community inherits from the EasyPack class. The EasyPack class inherits from overlay class. Overlay class inherits from task manager. So every community is a task manager. Okay, let me go back to the documentation, and somewhere shows in some cases tasks. It explains that community integration for your convenience. Every community is I will try to avoid spawning any task in the init of the community. Yes, I think this is yeah, the explanation about why task manager is necessary. In between another community initialization, working with a half initialized IPv8 may lead to problems. This practice makes the community more difficult to face. If you end up with a situation, then just cancel all pending tasks. Yeah, so the main reason we switch to the task manager architecture is just so that we don't load those different communities at different times. Okay, so let's see an example of how that would work. Here. Okay, yeah. This is going to take time, so let me just go through it at once. So this is a very simplified version of the NuNet adapter. So let's say we have a session class that inherits from the task manager, and it's going to create a session and start a community, right? But it's not going to start a specific community. It's just going to load multiple overlays. So okay, I have to install the Python extension, but so this function is basically in here. Load IPv8 overlays. Where is that function? Let's find it. Oh, here it is. Load IPv8 overlays. Then let's make the IPv8 community loader. Load. This IPv8 community loader is the IPv8 community loader class. I think it comes from here. Where is the, oh, sorry, that's the loader. So register default launchers and click community loader. And at some point, we have to load this load modules. Yes, here it is. So register default launchers, then we're going to pass the loader itself. So this function register default launchers is in load modules. Here at the end, register default launchers, and it's going to accept the loader that we passed on it from the session. And it's going to print community launcher. Let's go. Okay, it's not working, but here it is. So we have decorators for all the communities that we're going to load. So let's say, yeah, let's take this three communities as an example. So we have the default discovery community. It's basically decides how many peers we're going to be introduced to the strategy for going through the network and everything, and we're not going to edit anything out of it. Then this is also the default community. We didn't change anything. All these communities are within the IP-based library. So the example I wanted to show is with this print peer community. So let's go to this. Yeah. So IP-based community launcher, which is every community launcher that we're inheriting from. So when you just call it, it's what it does is one of them is get overlay class, and what it does is it just imports the new community that we built separately, just similar to the one we had here, the one we had here with the my community. But basically, we're just going to implement it in a different on a class of its own, and we're going to load it with the community launcher, so that the task manager can use to schedule it. So when this committee, right, this committee is the same as the one we saw earlier. It just says I am this peer and I know these peers. But extra to that, it's just going to print information about the network. By the way, you can find this this code on GitLab within the miscellaneous experiments group under protocol engineering under NuNet IPv8. So everything is here. Okay, let me go back to here, and yeah, since it's been more than an hour, let me just run it, and see the results of it. Basically, it's going to function similar to how we had a single overlay, but then it will make it much clearer when we are considering the metadata. Okay, so I can so let me get first import. So let's first create an object for this session. First launchers, then we have the from the session we have this start function. since it's asynchronous, that's why we're doing this. So it was launched, and basically the community has been loaded correctly, and it's running. So since it has a different community ID here, it's not going to see anyone until we launch a similar one. So let me just maybe bring that. Bring this one here, and maybe let's copy. Just a second. Copy it. Let's copy. It's a small one. And 50 megabytes. Should we wait or attempt a different copy method?
Will we have time for questions, Dago?
Yes, yes. I'm actually about to finish. Just 5 minutes. I just wanted to show this
Yeah, sure.
modular architecture because it would make it much easier to take a look at the metadata.
Okay.
I should have copied with star. Sorry. Right. Oh, yeah, no, it's going to take forever. Let me just start it. Okay. So we have the copies now. Yeah, let me run the same thing as I did here. Let me close this one. I sorry. I didn't give the second one. Okay. Okay, sure. Let's start. Okay. So and we've launched with the okay, I'm assuming since I'm connected to both the Wi-Fi and the line, my local laptop here is working through the Wi-Fi, which is a symmetric NAT, and that's why I think it's not able to communicate, which is actually a good demo for us. Let's try. I'm going to disconnect the Wi-Fi, and Hyper-V8, actually that's the best thing about it. If you change your network, it's going to adapt very quickly. So I'm disconnecting the Wi-Fi. Now you can see that it's down. I'm going to disable the Wi-Fi itself. Hopefully, if you connect, that would be really good. Because they should be able to communicate now. Like they should be able to find each other. I'm not behind the semantic NuNet, so I'm going to restart it. Oh, okay. I can see now that the bootstrapper that was configured is not the default one. It's a server that I have here. It's this one. I already launched it, but apparently maybe it's not working. Let's connect to it and check again. I'm guessing it's some IP table issue. No, it's not. Default policy is accept. Oh, wait. There was a problem with the first implementation. Yes, there was a fix that table was found. I'm sorry about that. For that part. There was a branch task manager. Yes. Let's. I'm sorry, I don't know how we're going to compare it. But maybe let me clone again. Just a second as well. It's the SSH. Just 1 second. Just one. Okay. Let's try this one. Let me add this one and send it there. Just remember there was a bug. Okay. Okay, let's try with this one. What is the main? Okay, nice. Well, we don't have to do it by hand. Okay, let's try with this. Okay, there was an error. Can we just take a look at this one? Not sure why it's not working, but let's leave the. Okay, it's not working here as well. Okay, there is a problem. Sorry about that. But what I wanted to show was the architecture. If it was running, that would have been great. Okay, I see a couple of differences. There are a few differences. It's more here. Yeah, okay. Let's go to the metadata. Save time. Sorry about that. Okay, so yeah, the metadata is also built with this logic. So we have the session class, which is basically going to use the community loader to load the communities. So if we go to the load module, we're going to have this same function that we saw earlier, and we have these communities: the NuNet community launcher, the discover the center, and the relay community. So they all do their own stuff. So this NuNet relay community is what's responsible for acting like a turn server, as we discussed earlier. So that's one community with just one responsibility. This NuNet community was created for the same as the relay one, but it serves as a parent class for the other ones. Basically, it's those functionalities specific to NuNet. So relaying, shell communication, and all those things. Yeah, so we have the DHT community and everything. So each community has its own definition. So for example, you can say the relay community is defined just the same as we defined the print peer community. It just, the difference is it has message handlers when it receives messages. And basically, the relay is going to advertise itself, and other peers that are not able to send messages are going to send it a message, and it's going to send those messages on behalf of them. And yeah, we have the shared registry, which basically acts as the DHT. So it's just a table which contains the node IDs, peer addresses, peer metadata, and tokenomics information. And it's basically used in the discovery, I think. Yes, in the discovery peer community, we have the DHT community and the shared registry, so that we can update the registry with functions such as let's say remove outdated peers, and yeah, you get the idea. So I think, yeah, I think we can.
You are muted. Should we hear you?
Hello. Yes, yes. How long was I muted?
Well, actually, after you just close the screen, it was muted.
Okay.
So
right.
just
okay. So there are questions.
All right. So we are slightly behind the schedule. But so I believe that so Dagim, you will post. First of all, we have all the code of this demo, and you will post it, and we can ask questions also based on that code. So I wanted, I mean, on the, yeah, we can ask questions sort of offline too. Yusra, did I hear somebody? But I wanted to kind of summarize slightly from the architectural perspective. So this is something that we'll have a talk next week about NuNet architecture, but basically this peer-to-peer networking is pretty much essential for us to build the decentralized architecture that we want to build and to allow machines behind NATs and kind of different machines to communicate to each other. So the whole thing that Dagim presented was from the IPv8 perspective of this protocol. From the architectural perspective, it's not that we are married to IPv8, but we are pretty much married to the P2P communication. So I think we were researching quite a few before we sort of converged to IPv8 for the private alpha. I think, if I remember correctly, it was IPv8. It was libp2, to some extent libp2p, WebSockets, WebRTC, and pretty much anything that we were able to use in order to do the functionality that we wanted. And in the future, we may change the protocol, but we will not change the principles. So this is something that I wanted to kind of say. And since the principles are pretty much, I mean, they're similar in peer-to-peer communication, so this is important to kind of to understand what we're doing and why we're doing that. All right. So, is there any comments, questions before we wrap up and sort of put that into somewhere in the wiki so that everybody can access and look and ask questions based on that?
Yeah, I'll be sharing the recording as well, on the day of challenge.
All right. So that's it then. Thanks a lot, Dagim. Thanks a lot for that, and everybody for participation. And see you soon. Bye.
Soon, yes.
Thank you. Bye.
Thank you, Dagim.